Thanks for the introduction. My name is Harikrishnan, and I'm going to talk about a sensor for trichloroethylene, which is a chemical pollutant that's found in water bodies. This is the kind of the outline. I'm going to talk about the problem out there, which is water bodies being contaminated by chemicals, mostly trichloroethylene and VOCs, which stand for volatile organic compounds like acetone and things like that. A little bit of background about the current detection methods that's out there, the solution we propose, how does the solution, that's the sensor, work, a little bit of material characterization of the sensor, the results, the proposed mechanism by which we think the sensor is working, and finally the conclusion. Why are we interested about volatile organics or trichloroethylene? Why do we need to detect it? It has come up very recently, this issue. It's VOCs or trichloroethylene is a carcinogen, and it's been found in many of the water bodies around the US and around the world also. 6% of the urban wells, 1.5% of the rural wells have VOCs in them. Trichloroethylene has been found in about 1,400 US military installations. In as recent as the last 2 years, there's been a bunch of lawsuits because of this contamination. And one of the biggest concerns is that we don't know how much is the extent of this pollution. It's only been found last few years, 1 to 2 actually. The possible reason is that the current solution or the gold standard is GCMS, gas chromatography mass spectroscopy, and it's an centralized detection system, which means you have to go out there in the middle of US, all those water bodies, take water samples, come back, do the test. And that's not really an solution, because you have such a wide sample to test. So that's why we need some kind of handheld point of use sensor, which you can just take in the middle of nowhere and test water samples. And trichloroethylene, there's been some existing work in sensing, mostly for atmospheric sensing of trichloroethylene. It's been found in some paints that's been used in indoors. So they've been looking for that trichloroethylene in gas samples, basically in nitrogen, oxygen, and argon as a carrier gas. And they have a few of them have reported limits of detection down to 1 parts per million. But the operating temperature of these sensors is 100 to 400 C, which means those are power intensive. You cannot, it's hard to make them a point of use. It's power hungry. For trichloroethylene detection water, again the gold standard is GCMS, which is again not point of use. The reason there's not many trichloroethylene water-based sensors is that you cannot have an electrochemical sensing, conventional electrochemical sensing based on TCE, because your trichloroethylene reduction potential is much higher than water. So if you apply a voltage, before you see a signal for trichloroethylene, water would just break up into hydrogen and oxygen. There's been some significant work on using microbial membranes sensors, basically embed some microbes which convert to TCE and detect them, but these have a very long response time, and they don't have a long shelf life period. So that's why we come up with a solution which we think works. It's basically using titanium nanotubes, which is nothing but titanium dioxide in the form of nanotubes on a titanium metal substrate. So titanium nanotubes are nanostructured, which means you have a very high specific surface area, increased diffusion, which is really good for detection. So we embed them with platinum, and then so you have a metal oxide semiconductor, which we think is the reason the sensor works at in a room temperature, gives a room temperature response to gas sensors. So this is the basic working principle. You have an titanium nanotubes right there on a titanium substrate, titanium metal substrate. The golden thing, that's your platinum functionalized on the nanotubes, and then you have an potentiostat readout. So basically, when your trichloroethylene reacts with your sensor system, what basically happens is you get a change in current, as simple as that, and that is indicative of the presence of trichloroethylene. This is the lab setup, kind of to prove the proof of concept. What you have is the air as an carrier gas, basically passed using a flow controller to control flow rate, and then your baseline is basically just passing air through your sensor, which gives you the baseline current, which forms the baseline. And after some time, air is cut off, and then instead it's passed through your sample, which is trichloroethylene in DI water at different concentrations, ranging from 0, which means there's no trichloroethylene, to 1000 ppm trichloroethylene water. So air at 120 SCCM is purged, so it's a carrier gas. So it kind of carries your trichloroethylene water vapor with it to your sensor. And when this happens, we do it for 15 seconds. You see a change in current. The signal would be your current when trichloroethylene air water vapor is passed over the sensor, divided by your baseline signal when just air is introduced. So these are the fabrication methods. One key thing with this is we don't use any clean room technologies. Many of the sensors out there use clean room methods. The actual method by which we make titania nanotubes is a pre-existing reported mechanism. You just dip your titanium metal strip in an electrochemical bath, you apply potential, and basically you would have growth of these tubes. They're pretty uniform size. You can actually control the length and the diameter of the tubes by controlling the time for which you anodize it and the voltage you apply. And subsequent to that, you anneal them in oxygen at 500 degrees C. This would change the structure from amorphous to crystalline. I'll explain why that is important. And subsequently, you deposit platinum on it. It's again a non-clean room based technique. What you do is you dip the whole system in a chloroplatinic acid, which is an acid of platinum, and then you shine UV light on it. So your platinum would just get deposited on your tubes. You can control the amount of platinum that's deposited by the amount of time for which you apply UV light, also the intensity of the UV light. So it's a pretty simple method of making the sensor. This is the SEM image of it's a 1 micron scale. So you can see the tubes, pretty uniform diameter holes, and the stuff that's right here that looks like dirt is platinum that's deposited on your tubes. To confirm the deposition of platinum on the titania nanotubes, we ran an EDAX on it. That's energy dispersive X-ray. So you can see the presence of platinum on the material along with titanium and oxide. There's also a little bit of carbon, which is unique to the method we made it. We ran an X-ray diffraction on the material, because I said we anneal them to make sure it's crystalline. The reason is that for most gas sensing applications, it's been found that crystalline states are the key and amorphous don't work. So we ran an XRD to confirm the crystalline state of titanium dioxide. So this is the actual sensor response. Your baseline, that's region 1, is when air is passed over the sensor. You don't see much significant current. And at 460 seconds, you cut the air out. Instead, you pass air through your water containing trichloroethylene, and then carry it over to your sensor. And you do that for about 15 seconds, at which you see an increase in current. And then at this point where you cut it off, your signal still increases, and within about 40 seconds you see a maximum signal. So that's your actual signal, the maximum response. Your actual signal is a ratio of your sensor response when TCE water is introduced to your sensor baseline current when there's just air. So that's a TCE signal. That's your 0 ppm parts per million, which is, we don't have any, just bare water passed over the sensor. It has a slightly higher signal at 10 ppm and 100 ppm. It can detect from 1000 to 10 ppm. We tried higher than 1000 ppm, and the signal, we weren't getting a higher signal, and I kind of proposed a mechanism by which we think it doesn't work for very high concentrations of TCE. So trichloroethylene reacts with O- ions. So basically your titanium nanotubes have chemisorbed oxygen on it. Basically oxygen gets absorbed on the substrate and O- ions are present. So your TCE reacts with these O- ions and you get electrons being formed, an excess of electrons. So the pooling of electrons would lead to a change in conductivity. You get a higher current when TCE is passed. So in conclusion, the sensor detects trichloroethylene water. It's a very simple system. You don't need any clean room technologies. It can go down to 10 ppm in water-based systems, and the range is about 10 to 1000 ppm. And it's a very fast response time. It's about 40 seconds. And in terms of the future work, this is pretty cool. I just saw this. It's a TV series that comes. It's called Alphas. So this girl has an ability to look at your breath, and she can make out if you have a disease or not. And I thought that was kind of cool. So if you look at this clip. So what she sees is in effect a moist breath. It's basically air mixed with water, which has volatile organic compounds in it, and she kind of sees that the person has a condition which is like cancer or diabetes or tuberculosis. And this, so what we just made here is pretty much mimicking that. You have air that has water in it and also has volatile organic compounds. So in effect, you can use this mechanism, use this sensor to detect a bunch of other conditions for health monitoring and things like that, which is pretty exciting. And that's the other people who have worked on this paper at the Utah Center for Biomedical Microfluidics, along with the nanomaterial characterization facility at the University of Utah. Also thank the Utah Science, Technology and Research Institute for funding this project. Thanks.